Hello everyone. Now we'll be seeing the next topic. So next topic here is the exponentially exponentially weighted averages. So this topic is coming into the second unit of your syllabus. So where we are seeing about the gradient descent. Okay. So before that, we'll have to understand what is how we are calculating the algorithms where we are optimizing the algorithms. So first we'll be seeing the optimization of algorithms. That is, what are the ways of optimizing the algorithms that we'll be seeing. Okay. So for that, consider okay. Um, okay. Now I hope this is visible to everyone. Okay. Yeah. So for that, consider the daily temperature. Okay. In a particular place like London. Okay. For that matter. Okay. London. Okay. From last year record. Consider it as a last year record around some 2023 data which you are taking. Now you can see that the Jan data, Jan 1 data is considered to be you can say theta 1, which is nothing but you can say 40 degree Fahrenheit, or you can say 4 degree Celsius. Okay, so theta 1 is nothing but the each theta is nothing but the each temperature records that are be taken. Then we are having Jan 2 uh, data. It is something around theta 2. Okay, so this will be around 49 degrees. Okay, so there is a change. So you can say 9 degrees on Jan 2. Like that, you can take some May data, some theta k, or you can say some particular value. Okay, where you can say that it is a 60 degree Fahrenheit. Okay, means that it's slightly warmer during May. Okay, then you can say theta k plus 1. Okay, which is nothing but 56 degree Fahrenheit. Okay, so all this uh, you can say the temperatures. Okay, you will be having. Okay, now um, these different temperatures. Okay, are being plotted into the graph. Okay, where you can see this is the graph, and this is nothing but your starting with Jan 1. Okay, temperature. Okay, these are the days. So x-axis is nothing but days. So you can say this is Jan 2, Jan 3, and this is nothing but mid of the year, around May, you can say. So this can be around May, and this can be end of the year like December. So what you can observe that um, during the starting of the year and during the ending of the year, okay, it is slightly colder, and during the middle of the year, it is warmer. Okay, so you can plot up the data, and you can see that that this would be the data from the entire year. Okay, where you can see on different dates. Okay, what can be the temperature. Now the trend looks like that this is the kind of uh, local average, or it's a moving average of a temperature. Okay, so you can see that there is also somewhat bit noisy in this case. Also you can see that um, it is not completely pure data. There are some noises in this particular data also. Okay, so for that reason, okay, we'll have to okay remove those noises. uh, so how to proceed, how to go about it? So what we do is, okay, To remove the noises, so we'll have to initialize, okay, something like you can say v0 equal to 0. Now what is this? So v0 is nothing but we are going to average with the weight, okay. It's nothing but the weight, we can say initializing the weight, which you can say, okay. So v0 is equal to 0. So we are going to average with the weight of zero point 0.9 times whatever is the previous value, okay, plus zero point 0.9 times that day's temperature. So that is nothing but v1 is equal to 0.9 v0, okay, plus zero point 0.1 theta 1. Now what is this? The This is nothing but the weight, zero point 0.9 times the weight, okay, and zero point 0.1 times the particular day's temperature. So this is how we are actually calculating. So the actual weight is nothing but the zero point 0.9 times the previous weight, okay, previous weight plus zero point 0.1 times the, okay, that day's temperature, okay. So here theta 1 will be the temperature on the first day, okay, first day temperature. So it is nothing but could you see that it is 4 degrees Celsius, okay. So my v2 will be, okay, it is nothing but zero point 0.9, okay, that's the zero point 0.9 times we are actually applying to the weight, which is nothing 0.9 v1 plus, okay, point 0.1 theta, okay, 2, okay. So this is for the second day temperature. For second day temperature, okay, I am applying the zero point 0.9 times the previous weight. So what was the previous weight? So this was the previous weight v1. Now in this case, the previous weight v0 is anyway is initialized to 0, okay. So when I write zero point 0.9 into 0 is nothing but it's 0. So zero point 0.1 into theta 1. Theta 1 is nothing but the first day temperature. Same way here, whatever you get it in v1 value, that is applied to this v2, okay. And we can say that zero point 0.9 times v1. So this particular value is applied to this plus zero point 0.1 into theta 2. Theta 2 is the second day temperature. Like that, we are continuing applied to zero point 0.9 v2 plus 0.1 theta 3. Okay. So we are doing this for vt, which is nothing but zero point 0.9 vt minus 1 plus 0.1 for theta t. So v is on a given day, okay, on a given day is zero point 0.9 times the v, 0.9 times v from the previous day, okay, weight, previous day weight, that is vt minus 1 plus the zero point 0.1 times we are adding to the current day temperature, current day temperature, which is nothing but theta t. That is what you could see here, okay. So zero point 0.9 times the previous day weight plus the current day temperature, that is zero point 0.1 times the current day temperature, okay. So if you compute this and plot them, okay, you get this red graph, okay, red line over here, okay. So as you can see that when I apply this formula, vt is equal to zero point 0.9 vt minus 1 plus zero point 0.1 theta t, okay, okay, what you get is the, okay, the this particular graph, where you can see that you get what you get is a moving average, or you can say the exponentially exponentially okay, weighted average of daily temperature, exponentially weighted average of a daily temperature. Okay, so you can see that how uh, uh, the weight is been exponentially changed. So the even the weighted average is actually moving exponentially on daily basis. That is on different temperature. Okay, so from this um, you can see that the previous how I have seen that zero point 0.9 VT1 VT minus 1 plus 0.1 T30. Okay, so I am applying the same thing. Okay, in this particular case, that is VT is equal to beta VT minus 1 plus 1 minus, okay, beta theta T. So what does this mean? This is nothing but the, okay, the weight from the previous one. Okay, and beta is nothing but the value, okay, that we are applying. So here you can see that beta value is nothing but equal to zero point 0.9. Okay, so what is this zero point 0.9? So this is what we are computing, okay, to the previous weight. So beta value what we are giving is nothing but zero point 0.9. So zero point 0.9 VT minus 1 plus 1 minus beta is nothing but zero point 0.1 theta T. Okay, so this is how we are actually calculate. So this zero point 0.9 is nothing but your beta value. Okay, that is nothing but the exponentially we are calculating the uh, we are applying to the previous weights. Okay, so beta value is actually applied to the previous weight. So if we compute this, so VT will be averaging approximately over. So you can say that VT will be, okay, will be 1 minus beta of day's temperature, of that day's temperature. Okay, so if we are calculating, okay, so we'll get VT is nothing but equal to 1 minus beta of day's temperature, of that particular day's temperature. Okay, so that is nothing but, okay, 1 by 1 minus zero point 0.9, which is nothing but 1 by 0.1, which is nothing but 1 by 10, which is nothing but 10. So that is nothing but for beta, if you are taking beta is equal to zero point 0.9 as the value. Okay, so we are taking roughly, we are taking the 10 days temperature value, 10 days temperature. So what you can see is that, okay, as you can see that whatever the beta value which you are taking here, now here I have taken the zero point 0.9 as the value. This beta value is nothing but it which tells the, okay, for how many days, okay, value you are taking into consideration for calculation. Okay, for how many days value you are taking, okay, for into consideration. So you can, this is nothing but the this is calculated by Vt is equal to 1 minus beta days temperature, where beta is nothing but the, okay, I have taken it as 0 0.9. So 1 minus 0 0.9, okay, which is nothing but equal to 1 by 0.1, 1 by 1 by 10. So beta is nothing. When beta is equal to zero point 0.9 means I am taking the 10 days temperature. Okay. So that is roughly which will be used, okay, for calculation of the 10 days temperature. Now if your weight is zero point 0.9, you can think that this is an average, this is averaging over 10 days temperature, which is in the red line. So you can say that this is nothing but for 10 days. So this can be the that in this particular case, so this is the average temperature which you are taking for last 10 days. Okay, that is for point 9 weight. You can think that, okay, that the graph for last 10 days, okay, the temperature was somewhat like this. Okay, so if beta is nothing but 0.98, 0.98, then it is nothing but 1 by 1 minus 0.98, which is nothing but 1.1 by 0.02, which is nothing but 1 by 2 by 100, which is nothing but 1 by 1 by 50, which is nothing but 50. So if I increase my beta value from zero point 0.9 to 0.98, so it is nothing but the 50 days temperature. That is, if my beta value is 0.98, then roughly it will be the 50 days temperature value. 50 days temperature value is taken into consideration. Okay. So when you're taking a 50 days temperature value into consideration, then you can see that there is a slightly improvement. You can see that there is a varying of the line. You can see that a finer line you can see than the previous one. So this is nothing but the for the beta is equal to 0.9. This is nothing but for your beta is equal to 0.98. Okay, you can see a finer line. You can see. Okay, so you can see a smoother line. Smooth for a smoother beta value, you get this. But on the hindsight, okay, the average is much larger. You can see the average. You can see this is the average value, but it is much larger than the red. So here you can see the average temperature or window, okay, for this is much larger than the red value, okay, which you can see in the graph. Okay, so if my beta is equal to consider, okay, 0.5, so what happens again? 1 by 1 minus beta is nothing but 1 by 1 minus. So I am actually here, what I'm doing here is I'm reducing. So when I'm reducing, it will become 1 by 0.5, is nothing but 1 by 5 by 10, which is nothing but 1, 2. So it will be nothing but 2. So it is nothing but 2 days temperature. When I'm saying 2 days temperature, then you can see that, okay, if you plot this, we get a yellow graph over. So this is nothing but your beta is equal to the 2 days. Okay, or you can say when your beta is equal to 0.4, where you're getting the averaging over the 2 days. Okay, and you can see the much shorter window. That is how much you'll get the more noise. Okay, more noise in this case. Okay, and it is much susceptible to the outliers, which you can see more susceptible to outliers, but it adapt to the quickly to the temperature change, because here you can see that the beta values is very small, zero point 0.5, that is for 2 days. Okay, temperature I am actually taking. So 2 days means every 2 days your new temperature will be recorded. So if you're saying beta value is higher, like zero point 0.9, so it will be like 10 days. If a 0.9, it is 50 days. So you can see that already temperature, okay, gap is more, that is over 50 days. But you can see that um, the average, that is the what is being taken is much larger, and you might not get the accurate value. But here you can see that you will get more accurate value if you're taking the beta value a bit smaller than if you're taking the beta value to be zero point 0.9 or 0.98. Okay, so overall the formula, okay, which you will be using is Vt is equal to beta Vt minus 1 plus 1 minus beta theta t. Okay, so this is the formula used for exponentially weighted average. Okay, formula used for exponentially weighted average. Okay, so if your weight is exponentially increased, you will get a smoother graph. If your weight is exponentially decreased, okay, if you are decreasing the weight, then you'll get a okay, more noise and more outliers. Okay, so we have to choose which is better, okay, which we get slightly better effect. So based on the the given data, you have to choose. So which one you have to take, whether it is beta to be a higher value or lower value, it should be taken based on the given data. So this is about the, okay, the exponential weighted average. So in the next video, we'll be seeing the gradient descent with momentum. Okay, thank you.